last time we were solving systems of equations using back substitution. Now we're going to solve them using matrices, using essentially the same thing that we did last time, except now it's going to be organized in a matrix form. So first of all, matrices have rows and columns. So suppose I have matrix A. We name a matrix with a capital letter, and it's got entries 3, 2, -4, 0, 5, 1. Okay. Rows go left and right, so it's got 2 rows. Columns go up and down, so it's got 3 columns. We give the dimensions of a matrix as rows by column. So this matrix A would be a 2 by 3 matrix, right? It's got 2 rows and 3 columns. Yes, you can have a matrix that's all 1 row. You can have a matrix that's all 1 column. We usually write the entries for the matrix in general as A11, A12, A13. So row 1, column 1, row 1, column 2, row 1, column 3. They all have unique locations in there. Row 2, column 1, row 2, column 2, row 2, column 3. Okay? If you have a square matrix, then it would be what we call an n by n matrix. So you would have as many rows as you have columns. So suppose you had a simple system that looked like this. You have x sub 1 minus 2x sub 2 is equal to 1, and you've got 3x sub 1 plus 2x sub 2 equals 11. From that, you can write what we call the coefficient matrix. The coefficient matrix is, well, just what it sounds like. It's a matrix full of coefficients. So in the first row, the coefficients are 1 and -2. In the second row, the coefficients are 3 and 2. Okay, so there's my coefficient matrix. Now, when you include the numbers on the other side of the equal sign, then you create what we call an augmented matrix. So an augmented matrix has a third column, and that third column has the numbers that are on the other side of the equal sign. So in this case, the 1 and the 11 are also in there. Okay, so we usually read it across 1, -2, 1, 3, 2, 11. Sometimes you'll see a little dashed line in between to indicate that the coefficients are on one side, and then the numbers on the other side represent the other side of the equal sign. So suppose I would like to solve this matrix by Gaussian elimination. So my first goal is to get rid of that 3 that's on the bottom left corner. So how do I do that? Well, I want something to go into row 3. All right, that's row 2. I'm looking at the 3. I want my answer to go into row 2. So if I take -3 times row 1, add it to row 2, and put the answer in row 2, then I think we've got something to work with. So let's try that. Let's take the first row and multiply it by -3. So I get -3. -2 times -3 is +6. 1 times -3 is -3. The bottom row, it remains 3, 2, 11, and now add them together. Those go away. 6 plus 2 is 8. 11 minus 3 is 8. So my next row, remember we are only putting this in row 2, so row 1 stays the same. Row 2 becomes 0, 8, 8. All right, well, I would like 1s in what we call the pivot points. The pivot points being the leading coefficients, so here and there. So if I take row 2, divide it by 8, answer goes in row 2, we'll have gotten there. So I get 1, -2, 1, 0, 1, 1. All right. At this point, this is in row echelon form. And I got to row echelon form by using Gaussian elimination. When you get to this form, you can go back and substitute and find that x sub 2 is equal to 1, and then put it in the row ahead of it and find out what x sub 1 equals. But suppose you wanted to be able to read the answer right from the matrix. For that, you're going to need a second process, and that is, how do I get rid of that -2 that's up in the top? So if I want to get rid of that -2 that's up on the top, I need something down the bottom that's +2 to balance it out, and I want my answer to go in row 1. So let's take row 1 and add double row 2 and put the answer in row 1. All right, so row 1 is 1, -2, 1. Double row 2, and I get 0, 2, 2. Okay, that becomes a 0, and I get 1, 0, 3 when I add them together. So now my first row is 1, 0, 3. My second row remains unchanged at 0, 1, 1. All right. This in here is called reduced row echelon form. Because if you notice what's on the left-hand side, I've got 1s running down the diagonal here and 0s everywhere else. Now, I realize it's only a 2 by 2 matrix, so 0s everywhere else. There's only 2 other spots. But much bigger matrices will have 1s running down the diagonal and 0s everywhere else. We actually have a name for this. Next chapter, I think we'll get to be calling this the identity matrix, where it's got 1s down the diagonals and 0s everywhere else. What that means is that I can solve the system right away. I know that x sub 2 is equal to 1, and x sub 1 is equal to 3, so these two lines intersect at the point 3, 1. There's a name for this second method, and it's called Gauss-Jordan elimination. All right, so when we solve by Gaussian elimination, we end up with something in row echelon form, meaning that we've got that stair-step pattern. We can go and do back substitution, and we'll get an answer. If we go all the way down and create 0s everywhere else except down the diagonal, we have 1s, then we've done Gauss-Jordan elimination, and we end up with an answer in reduced row echelon form. So let's take a look at a 3 by 3 version of this and see if we can solve a system that's 3 by 3. So suppose I have a system that looks like this. 2x sub 1 plus 4x sub 2 minus 2x sub 3 is equal to 2. I've got 4x sub 1 plus 9x sub 2 minus 3x sub 3 is equal to 8. And then I've got negative 2x sub 1 minus 3x sub 2 plus 7x sub 3 is equal to 10. All right, so there is my system. I've got 3 equations and 3 unknowns. That means there's a possibility that I could come up with a nice single point where all 3 of those planes intersect. All right, so the first thing I want to do is I want to set up the augmented matrix. All right, my augmented matrix will look like this. I'll put the coefficients across the row, 2, 4, negative 2, 2. The second row will be 4, 9, negative 3, 8. And then negative 2, negative 3, 7, 10. All right. You're going to double check to make sure that you copied the numbers down correctly from the problem, because you will kick yourself if you get all the way to the end and realize you got the wrong answer because somewhere in row 1 you didn't copy the numbers correctly. And I'm probably going to do that at some point too, except I can edit my video and you can't edit your test questions. So double check your work before you get too far. All right, so what's my goal? My goal, first, if I'm going to do this by Gaussian elimination, is to get rid of the 4 and the negative 2 over here, the negative 3 here, and get my leading coefficients to become 1s. So I may start doing more than one thing at a time, because you notice as these matrices get bigger, the problems get longer to do. And at the beginning, I was writing out every single step. Maybe I don't need to do that. So the first thing is I want to multiply row 1 by something and add it to row 3 to get rid of what's in row 3. Well, that's easy, right? I've got a 2 and I've got a negative 2. So if I just add the two of them together, if I add row 1 to row 3 and put the answer in row 3, that'll create a 0 in the bottom left corner. Now, if I multiply the top row by negative 2 and add it to row 2, answer goes in row 2. You notice now that 2 will become a negative 4. Negative 4 plus 4 gives me 0. So I'm trying to add multiples of one row to another to get rid of certain values. So when we add these rows to each other, let's see what we get. The first row remains the same, right? That doesn't change. So I still have 2, 4, negative 2, 2. And then the second thing doesn't change either, right? If I take row 1 plus row 3, 2 plus negative 2 is 0, 4 minus 3 is 1, 7 minus 2 is 5, and then 10 plus 2 is 12. I put up on the top here what happens when I multiply row 1 by negative 2. So 2 times negative 2 is negative 4, 4 times negative 2 is negative 8, negative 2 times negative 2 is positive 4, 2 times negative 2 is negative 4. So let's take the 4 red numbers on the top and add them to the 4 numbers in the middle row. So 4 plus negative 4 is 0, 9 minus 8 is 1, 4 minus 3 is 1, and 8 minus 4 is 4. All right, now I've got zeros in the bottom left corner. Let's work in the other direction. So now let's work to get rid of that 1 that's in row 3. Well, that one's actually pretty easy, because if I take row 2 minus row 3, answer goes in row 3, I think that'll take care of it. All right, so I keep my top row. I've got a 2, 4, negative 2, 2. I keep the middle row 0, 1, 1, 4. And now 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 5 is negative 4. 4 minus 12 is negative 8. Did I just say 1 minus 1 was 1? I said 1 minus 1 was 0, and I wrote a 1 in here. Okay. There we are. Beautiful. All right, so now I can take that third row, and I can divide it through by negative 4. All right, when I do that, I'll create 1s in the pivot positions. And at the same time, by the way, I can go up to that top row and divide it by 2. So take row 1, divide it by 2. Answer goes in row 1. Take row 3, divide it by negative 4. Answer goes in row 3. So I get 1, 2, negative 1, 1, 0, 1, 1, 4, 0, 0, 1, 2. Okay. Now at this point, my solution is in row echelon form. Why? Because I've used Gaussian elimination. It's in that stair-step pattern. I can go back and substitute and say x sub 3 is 2, go back to find x sub 2, go back to find x sub 1. But what if I want to go all the way through and solve it so that I have a diagonal of 1s on the left side and the solutions essentially to the system on the right? What I want to do is I want to put it in what we call reduced row echelon form. And so for that, like for row echelon form, I worked from top to bottom and then left to right to get the zeros. Now this time I'm going to work from bottom to top and from right to left to get those zeros. All right, so let's try that. Let's get rid of the 1s that are in that third column. And let's do this in a way that doesn't put the numbers back where we already found the zeros. So for example, I could take row 1 and row 3, add them together and put the answer in row 3. But that's going to create 1s in that spot that I just got rid of, right? The same thing if I added row 1 and row 2 together. Well, sure, I'd create a 0 over here, but then I'd create a 1 over here, and I don't want that. So I got to be very careful that I don't start reinserting values where I had values that I got rid of before. So let's say I took row 1 and row 3, added them together, and put the answer in row 1. That's pretty safe because I already have values here, and I don't have to worry about reinserting them. I never got rid of values there. So let's do that. Let's take row 1 and row 3, put the answer in row 1. So 1 plus 0 is 1, 2 plus 0 is 2, negative 1 plus 1 is 0, 1 plus 2 is equal to 3. Okay. Now, I want to put something in row 2. But again, I don't want to reintroduce things that I just got rid of. So it looks safe to combine row 2 minus row 3 and put the answer in row 2. So 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 4 minus 2 is 2. So I'm taking row 2 minus row 3. Answer goes in row 2. And then row 3 stays unchanged. 0, 0, 1, 2. All right, so I've gotten rid of the coefficients here in the third column. Now I've got one thing left to do, and that is that 2 that's over here. Again, let's work carefully so that we don't reintroduce things back to spots that we had already cleared out. So it looks like if I want to put an answer in row 1, that I should take row 1 minus 2 times row 2, and that leaves me with only entries going in row 1 and nowhere else. So 1 minus 0 is 1. 2 minus 2 is 0. 0 minus 0 is 0. Now just watch those coefficients on the other side. I've got a 3 minus 2 times 2, and that gives me negative 1. All right, the second row remains the same, and the third row remains the same. And now we have a name for this form. We call it reduced row echelon form. And the process that I use to get here is called Gauss-Jordan elimination. The advantage of using this system is that I have an answer. X sub 1 is equal to negative 1, x sub 2 is equal to 2, x sub 3 is equal to 2. I have a nice consistent system. That's where the three planes intersect. No back substitution necessary. I've worked my way through, I've gotten a solution, and I'm done. All right, let's take a look at one or two more cases. All right, so you can always use Gauss-Jordan elimination. It takes a little bit longer, but it's kind of nice to get that answer right away. All right, let's take a look at this system. Suppose I've got x sub 1 plus 2x sub 2 plus 3x sub 3 equals 4, 4x sub 1 plus 5x sub 2 plus 6x sub 3 equals 7. You'll notice the creativity that's going into these coefficients. 7x sub 1, 8x sub 2, 9x sub 3, equals 12. All right, so when I set up my augmented matrix to solve this system, I get 1, 2, 3, 4, 4, 5, 6, 7, 7, 8, 9, 12. Okay, first thing is let's get rid of the zeros under the first column. And so let's try to be efficient about this. If I do negative 4 row 1 plus row 2, answer goes in row 2. Negative 7 row 1 plus row 3, answer goes in row 3. All right, so the first row remains the same. 1, 2, 3, 4. If I multiply the top row by negative 4, then that gives me negative 4, negative 8, negative 12, negative 16. So now add these two things together, and I get 0, negative 3, negative 6, negative 9. All right, switch colors here for a second. If I multiply row 1 by negative 7, that gives me negative 7, negative 14, negative 21, negative 28. So the entries that go down here are 0, negative 6. If I do that, I'll get negative 12 and negative 16. Okay. Let's take those two rows down the bottom and get ones in the first position because, well, at least in the next row because they're multiples. So I'm going to get 1, 2, 3, 4. The next row will give me 0, 1, 2, 3. But then down the bottom, I'm going to get what? 0 I can at least divide by 2, or negative 2. That'll give me 3. Negative 12 divided by negative 3 is 4. Now, I got to divide by 2. That'll give me 6. And that'll give me an 8. All right, let's try creating a 0 down in this spot over here. Okay, so let's take negative 3 times row 2 plus row 3, answer goes in row 3. All right, so I'm going to keep my 1, 2, 3, 4. I'll keep my 0, 1, 2, 3. But now I'm going to take negative 3 times row 2, so negative 3. So so I'm back to where I was before. Negative 3, negative 6, negative 9. Combine that with 3, 6, and 8. And you notice I end up with 0, 0, 0, negative 1. Is that a good thing or a bad thing? Well, what does this mean down here? This means that 0 times the third variable is equal to -1, and that's not possible. Right? It's not possible to multiply something by 0 and get anything besides 0. So what that means is that there's no solution. Okay, so we always look for that stair-step pattern. We look for the ones down the diagonal. Here, I don't have a 1 down the diagonal. I have a 0 in the bottom. And sometimes it's easy to think, well, zeros are a good thing, right? If I just keep putting zeros in there, that cleans up my matrix. But you don't want to end up with a 0 as the coefficient. On the other hand, if you had a 0 and then another 0 on the other side, that's when you start setting up parameters. So let's say I had a system of 4 variables, x1 through x4, and I started solving the matrix, and it came out to look like this. 1, -1, 2, -1, -1, 0, 1, -2, 0, 0. And then as I continued to reduce them, I ended up with 2 more rows of the same thing. What does that mean? So I said I had 4 variables, so x sub 1, x sub 2, x sub 3, x sub 4, and this was my column on the other side of the equal sign. Well, if I combine those last 3 rows together, what I'm going to end up with is one complete row on the top, right? 1, -1, 2, -1, -1. I'm going to end up with a 0, 1, -2, 0, 0. But then I'm going to end up with 2 rows of all zeros. This is different from the case above. In the case above, we ended up with a 0 and a 1, and we said that was not possible because you couldn't let 0x equal 1. But here we end up with 2 rows that are all zeros. What that means is that there's a lot of different possible solutions. What am I going to do? Well, the first thing is I'm going to set up a parameter, and I'm going to let x sub 4 be that parameter t. But if I have 2 rows of zeros, I'm going to need 2 parameters. So let's go back then. If x sub 4 is t, then let's let x sub 3 be something else. Usually we use s as the next variable, and it works out because, look at the second row. I've got an x sub 2 and I've got an x sub 3. So now I can write x sub 2 in terms of x sub 3, and on the row on the top, I'm going to be able to write everything in terms of the other variables. All right, so x sub 4 is t, x sub 3 is s. Now look at row 2. Row 2 says that x sub 2 minus 2x sub 3 is equal to 0. Well, x sub 3 is s. So x sub 2 equals 2 times s, right? I just moved that over to the other side, replaced it with an s. And now the top row says x sub 1 minus x sub 2 plus 2x sub 3 minus x sub 4 is equal to -1. Replace everything with something that I've got. So I have nothing for x1, but I know that x sub 2 is 2s, and I know x sub 3 is s, so that's a 2s also. X sub 4 we said was t, and that gives me -1. Well, in this case, the s's happen to go away. That will not always be the case. Sometimes you'll end up with s's and t's in the same equation, and that's okay. Right? Carry this one step further. X sub 1 equals t minus 1. Right? So when I go to write my answer looks funny. It says x sub 1 is t minus 1. X sub 2 is 2s. X sub 3 is s. And x sub 4 is t. And that's a perfectly valid answer. It depends on 2 parameters now instead of 1. So in this case, there's an infinite number of solutions, but how can I write my solution set? I can write it in terms of 2 parameters.